What are logits? What is the difference between softmax and softmax underscore cross underscore entropy underscore with underscore logits? In the TensorFlow API docs they use a keyword called logits. What is it? A lot of methods are written like, if logits is just a generic tensor input, why is it named logits? Secondly, what is the difference between the following two methods? I know what tf.nn.softmax does, but not the other. An example would be really helpful.
The softmax plus logits simply means that the function operates on the unscaled output of earlier layers and that the relative scale to understand the units is linear. It means, in particular, the sum of the inputs may not equal 1, that the values are not probabilities. You might have an input of 5. Internally, it first applies softmax to the unscaled output, and then computes the cross-entropy of those values versus what they should be as defined by the labels. tf.nn.softmax produces the result of applying the softmax function to an input tensor. The softmax squishes the inputs so that some input equals 1, and it does the mapping by interpreting the inputs as log probabilities, logits, and then converting them back into raw probabilities between 0 and 1. The shape of output of a softmax is the same as the input. See this answer for more about why softmax is used extensively in DNNS. tf.nn.softmax underscore cross underscore entropy underscore with underscore logits combines the softmax step with the calculation of the cross entropy loss after applying the softmax function, but it does it all together in a more mathematically careful way. It's similar to the result of the cross entropy is a summary metric. It sums across the elements. The output of tf.nn.softmax underscore cross underscore entropy underscore with underscore logits on a shape 2,5 tensor is of shape 2,1. The first dimension is treated as the batch. If you want to do optimization to minimize the cross entropy and you're softmaxing after your last layer, you should use tf.nn.softmax underscore cross underscore entropy underscore with underscore logits instead of doing it yourself, because it covers numerically unstable corner cases in the mathematically right way. Otherwise, you'll end up hacking it by adding little epsilons here and there. Edited February 7, 2016. If you have single class labels, where an object can only belong to one class, you might now consider using tf.nn.sparse underscore softmax underscore cross underscore entropy underscore with underscore logits so that you don't have to convert your labels to a dense one-hot array. This function was added after release 0.6.0.
Short version. Suppose you have two tensors, where y underscore hat contains computed scores for each class, for example, from y equals wx plus b, and y underscore true contains one hot encoded true labels. If you interpret the scores in y underscore hat as unnormalized to log probabilities, then they are logits. Additionally, the total cross entropy loss computed in this manner is essentially equivalent to the total cross entropy loss computed with the function softmax underscore cross underscore entropy underscore with underscore logits. Long version. In the output layer of your neural network, you will probably compute an array that contains the class scores for each of your training instances, such as from a computation y underscore hat equals wx plus b. To serve as an example, below I've created a y underscore hat as a 2 by 3 array, where the rows correspond to the training instances and the columns correspond to classes. So here there are 2 training instances and 3 classes. Note that the values are not normalized, i.e. the rows don't add up to 1. In order to normalize them, we can apply the softmax function, which interprets the input as unnormalized log probabilities, aka logits, and outputs normalized linear probabilities. It's important to fully understand what the softmax output is saying. Below I've shown a table that more clearly represents the output above. It can be seen that, for example, the probability of training instance 1 being class 2 is 0.619. The class probabilities for each training instance are normalized, so the sum of each row is 1.0. So now we have class probabilities for each training instance, where we can take the argmax of each row to generate a final classification. From above, we may generate that training instance 1 belongs to class 2 and training instance 2 belongs to class 1. Are these classifications correct? We need to measure against the true labels from the training set. You will need a one-hot encoded y underscore true array, where again the rows are training instances and columns are classes. Below I've created an example y underscore true one-hot array where the true label for training instance 1 is class 2 and the true label for training instance 2 is class 3. Is the probability distribution in y underscore hat underscore softmax close to the probability distribution in y underscore true? We can use cross-entropy loss to measure the error. We can compute the cross-entropy loss on a row-wise basis and see the results. Below we can see that training instance 1 has a loss of 0.479, while training instance 2 has a higher loss of 1.200. This result makes sense because in our example above, y underscore hat underscore softmax showed that training instance 1's highest probability was for class 2, which matches training instance 1 in y underscore true. However, the prediction for training instance 2 showed a highest probability for class 1, which does not match the true class 3. What we really want is the total loss over all the training instances. So we can compute. Using softmax underscore cross underscore entropy underscore with underscore logits. We can instead compute the total cross-entropy loss using the tf.nn.softmax underscore cross underscore entropy underscore with underscore logits function, as shown below. Note that total underscore loss underscore 1 and total underscore loss underscore 2 produce essentially equivalent results with some small differences in the very final digits. However, you might as well use the second approach. It takes one less line of code and accumulates less numerical error because the softmax is done for you inside of softmax underscore cross underscore entropy underscore with underscore logits.
tf.nn.softmax computes the forward propagation through a softmax layer. You use it during evaluation of the model when you compute the probabilities that the model outputs. tf.nn.softmax underscore cross underscore entropy underscore with underscore logits computes the cost for a softmax layer. It is only used during training. The logits are the unnormalized log probabilities output the model. The values output before the softmax normalization is applied to them.
Mathematical motivation for term. When we wish to constrain an output between 0 and 1, but our model architecture outputs unconstrained values, we can add a normalization layer to enforce this. A common choice is a sigmoid function. 1 in binary classification, this is typically the logistic function, and in multi-class tasks the multinomial logistic function, aka softmax. 2. If we want to interpret the outputs of our new final layer as probabilities, then, by implication, the unconstrained inputs to our sigmoid must be inverse sigmoid probabilities. In the logistic case, this is equivalent to the log odds of our probability, i.e. the log of the odds, aka logit. That is why the arguments to softmax is called logits in TensorFlow, because under the assumption that softmax is the final layer in the model, and the output P is interpreted as a probability, the input X to this layer is interpretable as a logit. Generalized term. In machine learning there is a propensity to generalize terminology borrowed from math/stats/computer science, hence in TensorFlow logit, by analogy, is used as a synonym for the input to many normalization functions. While it has nice properties such as being easily differentiable, and the aforementioned probabilistic interpretation, it is somewhat arbitrary. Softmax might be more accurately called softargmax, as it is a smooth approximation of the argmax function,